In this video, we're going to look at CRA models for fraction division algorithms. There's going to be two algorithms that we look at. One will be the common denominator algorithm, and one will be the standard algorithm. The first one that we'll look at is the common denominator algorithm. I have this one written out here, and then we'll kind of show it with just the concrete model here. So for the common denominator algorithm, we're starting with 3/4 divided by 2/3. So with the common denominator algorithm, what we're going to do is find equivalent fractions for one or both fractions if we need to, such that our denominators are common or the same. Okay, so for 3/4 divided by 2/3, we're going to change this equation into change this expression into equivalent expression with common denominators. Okay, so we're going to change this into 9/12 divided by 8/12. Okay, so kind of showing what we're doing on the model, and I'll kind of jump back and forth here. So we're starting with 3/4. We want to divide this into groups with a size of 2/3. Okay, so we don't have thirds shown in the model, so this is one reason why we might do the common denominator algorithm. So first, instead of having 3/4, right, looking at fourths and thirds, I know that 12ths is going to be my common denominator. So I'm going to first represent this quantity as 12ths. Okay. So taking our 12ths pieces, so we're going to change this into, instead of 3/4, we're going to have 9/12. A little tricky to stack this one. Alright, so we have 9/12 there. Okay, so it's the same area as 3/4, so it's the same, it's an equivalent fraction, so it takes up the same area. So if I have 9/12 and then I want to create groups with a size of 8/12, and again, the reason why I'm making groups with a size of 8/12 is because 8/12 is the same size as 2/3. So these are our thirds pieces. You can see there'd be 4/12 in each. So for 2/3, there'd be 8/12. Okay. So I'm actually going to put these over here so I can show. I'm going to create groups with this size. So I'm just going to take these off and transfer them over. Okay, so we're using those 2/3 just to make sure that we are actually creating those groups with the size of 2/3. Okay, so there's one group. So we have one full group of 8/12 or a group of 2/3. It's the same thing because they're equivalent fractions. They take up the same area here. But then we have this one piece that's left over. So we have one group with a size of 2/3. Right, we start with 3/4, creating groups with a size of 2/3. We want to know how many groups with that size have we created. So here we have one. Right, so here I have the answer shown as 1 and 1/8. So that's my one full group. I have this one piece left over. Again, this one piece, right, I need 8 of these pieces to make up this whole group. So this is 1/8 of a group with a size of 2/3. Okay. I want to write one more thing on here for this abstract model too, right, because kind of what I had, this common denominator strategy essentially turns this into a whole number division problem, as you can see here. Right, I went from 9/12 divided by 8/12 equals 9 divided by 8. Right, so another way to think of that is, right, because these are just that denominator, right, that's the name of the part. So we can kind of think of that as the label as well. So since we have the same size parts in our dividend and our divisor, we can think of that as 9 divided by 8, and we're just keeping this label of 12ths as we go along. Okay, so that's why we're able to think of this as just 9 divided by 8. and that would be equal to either 9/8 or 1 1/8. Okay. All right, so that's the common denominator algorithm. Okay, so we can use that for any fractions. Once you can find the algorithm is for fraction division. You find common denominators, and then you ignore the denominators and just turn this into a whole number division problem. Okay, so that's one algorithm. Then we'll go to the standard algorithm next. Okay, so the standard algorithm for division, we have a length model that we'll look at for this one. Again, we're just going to do the concrete one just in the sake of time, but the representational models for both of these would just be, you could just do drawings that aligned with the concrete models. So it's the exact same problem, so 3/4 divided by 2/3, but we're going to use the standard algorithm. You might hear it called the invert and multiply algorithm or the keep, flip, change algorithm. There's kind of different names to remember it. But in this algorithm, we're going to, instead of dividing by 2/3, what we do for the standard algorithm is instead we multiply by the reciprocal of 2/3. The reciprocal is we just exchange the numerator and denominator. So we went from 2/3 and switch them to 3/2. Okay, so we're going to kind of use this model to explain why we're able to do the shortcut method, because then we just multiply across, use the standard algorithm for multiplication, so 3 times 3 is 9, 4 times 2 is 8, and that gets us to 1 1/8. Okay, so we'll use this model to kind of explain why we're able to, just flip that fraction for some reason and then change our sign from division to multiplication. Okay. So we have 3/4, so this is our starting amount, and we want to divide this into groups with a size of 2/3. Okay, so if we take our 2/3 pieces here, right, you can see, right, we can't only put 2 in there, right, because then it's not big enough for a group of 2/3, and here we have too much for a group with the size of 2/3. So we need to think of breaking this down in some way. So we need to represent this 3/4 as something else, so still that same length, but an equivalent fraction that has different size parts. Okay, so I'm going to show one that doesn't work and then show one that does work. So we kind of, the starting point is thinking of how can we break these yellow pieces, these fourths, into smaller portions and then see if it will match kind of these break lines for that group size of 2/3. So an easier starting point is think of, well, we'll just break these in half. We'll just cut each of these fourths into 2 equal parts. Okay, so those would be 1/8. Okay, so obviously we can represent our 3/4 as 6/8. Then if we're looking to see, okay, can we create groups with the size of 2/3 from this? Right, you can see that this break line is pretty much in the wrong spot, right? We need this to be able to be broken into groups with the size of 2/3. Here, the 6/8 is larger than the 2/3, but if we take away one of the eighths and just put 5/8, then it's not big enough to be a group with the size of 2/3. Okay, so breaking those fourths into 2 equal parts is not going to work, so we can try breaking into 3 equal parts. Okay, so each fourth, right, what we're doing is we're representing this as 3/12. Okay, so our 3/4 has been broken into, each fourth has been broken into 3 equally sized parts. So now we want to see, can we actually create groups with the size of 2/3 using these parts? Right, so you can see if we just take this one away, right, those lines are flush, meaning that this portion also has a length of 2/3. Okay, so then if we're looking at this, right, I'm just going to kind of separate this just a little bit. Right, so remember we started with this length of 3/4, so this total black length now is still representing 3/4. So we're going to create groups of the size of 2/3, which is the orange portion. So again, here's one group that has a size of 2/3. Okay, so that's our 1 for our mixed number. And then here we have one extra piece that's left over. And again, we would need a total of 8 pieces to make a full group with the size of 2/3. So this piece represents 1/8 of a group of 2/3. Okay, so relating this back to the standard algorithm, right? Why are we able to just multiply, invert this fraction and then multiply across? Why are we able to do that? Right, we'll look at, if we're looking at the numerator, right? Numerator is the number of parts that we have, right? So we used to have 3. We had these 3 yellow pieces. Okay. What we ended up doing was, instead of having 1 yellow piece here, we now have 3 black pieces that represent that same length. Okay. Same with the second fourth and the third fourth. So what we've done is we've tripled the number of parts that we have shown in our model. We've tripled the number in our starting amount. Okay, and again, that is the number of parts we have is the numerator. So we've multiplied our numerator amount, that 3, by the denominator of that divisor, by 3. Okay, so that's where we get this 3 times 3 on the top from, right? We went from having 3 parts to 9 parts representing our length. Okay, so that's our numerator there. Also, if we look at our group size, right, we originally had 2 parts that made up this whole, right? We had just those 2 parts that makes up the whole of our new group size. Okay, so I'm going to kind of move these down a little. So if we're thinking of this in this term, right, we had these 2 pieces. When we remodeled this length using these smaller pieces, right, we were also increasing the number of total parts that went into each of these thirds. Okay, so rather than having our new group size represented by 2 parts, right, we now have this represented by 8 total parts. So we've quadrupled that or multiplied that 2 and 4 together, right? So now instead of having 2 parts make up our group size that we wanted to divide this length into, we now have 8 parts, and again, that's that 4 times 2. Okay. So again, you can do the representational model for this one as well, right? This would just be, you can use like a number line or draw some different bars, but just in the sake of time, I just wanted to do the concrete and the abstract. But those are those 2 algorithms, kind of the common algorithms for fraction division. That first one being the common denominator algorithm, and then probably the one that we're more used to seeing is that standard algorithm.